So the first thing we're going to do in talking about circuits is introduce the basic circuit elements that we're going to be putting together to create circuits. So for starters, let's just deal with an ideal wire. And it is exactly what it looks like. It's represented as a line, and its function is to provide a path for current to flow. So currents flow along wires. Now, if you have an ideal wire, there's no resistance in an ideal wire. So obviously that's an idealization. For many circuits, treating the wires as ideal is good enough because the resistance really occurs within other elements within the circuit. A switch is drawn like this. So basically it's like you had a wire, and then we've usually got a couple of dots and then a line, and clearly what's going on is that switch is providing an opportunity to break the pathway. So if that switch is up the way that it's drawn at the moment, then the pathway is broken and current can't flow. If, on the other hand, the switch is closed, then basically it's just a wire, and then current can flow along that path. So an open switch, no current flows. A closed switch, current will flow. And so what will often happen in using a switch when we have circuit problems where we'll use a switch is that we will close the switch at time t equals 0. So we'll close the switch and start our watch at the same time, and then see what happens as various things change within the circuit after closing the switch. All right, the next one, battery. And so again, what we have is we have sort of the wires coming in on both sides, and then you can see the two terminals. And for a battery, the shorter end here is the negative terminal. The longer end is the positive terminal. So here's clearly a battery that's oriented so that its positive end is to the right, its negative end is to the left. The function of a battery is to provide the energy that's going to drive the current around the circuit. Next is a capacitor. And as you can see, a capacitor looks very similar to a battery, but the difference is that both lines for a capacitor have the same length. And so the capacitor's function is it's a place where we can store energy within an electric field. And so there are situations where we can get a capacitor to act like a battery in terms of providing a potential to drive a current. Those two symbols look a lot alike, but they represent two different elements. Next element's a resistor. And again, resistor is denoted by you got a wire coming in, and then effectively you just got sort of a line going up and down, and then the wire going out. So the resistor here is sort of the squiggly piece in the middle, and a resistor's function is to dissipate energy. So the resistor you probably know best is a toaster. And so when you put toast in a toaster and you turn it on, it drives a current through that resistor. That resistor heats up the coil element. That coil element, you see it, so it dissipates energy through. You see it turn red hot, and it obviously toasts the bread. Last of our major elements is the inductor. And so again, the inductor, you've got the wire coming in, and instead of a line going up and down like for a resistor, it sort of squiggles around, because as we will see, an inductor is basically just a wire that's wrapped around some cylinder. And so that's what this picture is trying to designate. The function of an inductor is to store energy in a magnetic field. So what you can see is we've got three elements here that have the ability to provide energy. So a battery does, the capacitor and the inductor can't, because they're places where you can store energy, so they can also be places that provide energy. The resistor, on the other hand, it's purely just going to dissipate energy. So a couple final elements to introduce. The first two of these are measuring devices. So the first one's an ammeter. And an ammeter measures the current through a particular branch of the circuit. And as we'll talk more about within the next few videos, an ammeter you can treat as having zero resistance, and so you can place it in series in your circuit so that the current that's flowing through whatever branch you're interested in measuring the current will flow right through your ammeter, and that's how it measures it. The next one's a voltmeter. And so what a voltmeter measures is it measures the potential difference between 2 points in the circuit. So a voltmeter is going to have two leads. You put one on one side of an element, you put one on the other side of the element, and they'll tell you what the voltage drop is across that element within the circuit. A voltmeter we treat as having infinite resistance, and it's placed in parallel. And so we'll describe what it means to be placed in series and placed in parallel a little bit more in the next couple of videos. But these are our two effectively measuring devices. They're keeping track of the current within the circuit and the potential drops around the circuit. And then the last element we've got is a ground. And so a ground, its function is to provide some sort of conducting path for excess charge to flow. Now, why a ground is useful is because if that excess charge builds up, it can either end up shorting out the circuit, it can end up creating shocks, it can at some point end up overheating things to the point where you actually end up with dangerous situations from your circuit. So grounds are typically fairly important from a safety perspective. So we can put all these elements together into a circuit. And so what you'll notice is we can find each of the elements that we were just talking about. So let's start. There's our battery. And again, the battery is sort of going to be defined by providing some voltage that's going to drive the current around the circuit. In this case, I happen to have 3 resistors within the circuit. So these here are my 3 resistor elements. I'll label them R1, R2, and R3. I also happen to have a capacitor and an inductor. And so again, those are sort of the 3 major elements that we'll tend to focus on in terms of combining into these circuits that we hook up to a battery. I've got my 2 measuring devices, and then I've got my switch. So my switch, that's going to allow me to create a pathway to current for current to flow, or I can break that pathway by opening the switch up. And then again, I can measure the current within a circuit with my ammeter. So here it's placed in series with the elements R2 and L1. So it's going to tell me how much, this ammeter will tell me how much current is flowing down this branch of the circuit. And then my voltmeter is connected across this particular resistor. So you can see where I've got one lead here, I've got the other lead of the voltmeter there, and so it'll enable me to figure out what the potential drop is across resistor 3. So for those 4 key elements, battery, capacitor, resistor, inductor, each of them has a fundamental quantity that defines what they are. So for the battery, it's the potential difference of the voltage, and that has SI units of volts. The capacitor, its key quantity is capacitance. And so the SI units for that are farads. That's just a short version of Faraday, for Michael Faraday, who was one of the big key inventors in figuring out a lot of the stuff that goes on with electricity and circuits. The key quantity for a resistor is its resistance. So how much does it resist current flowing through it? And the SI unit for that is the ohm. The symbol we'll use is the Greek capital omega. That's standing for the ohm. And then the inductor, its key quantity is inductance. And again, the SI unit for that is the Henry. So these 4 key elements, each of them has a fundamental quantity that defines it, and each of those has an SI unit that we want to make sure that we're using the right SI unit with the right key quantity.